I would like to introduce to you our NASA expert, actually. This is Stephen Cox, and today he will be talking about the Aurora Borealis. So please put your hands together and give him a big warm welcome, Mr. Stephen Cox.
Thank you all for coming. Is the bar closed or buffet or something closed? So this is actually the first time I've given this one. So I came on this cruise last year and was expecting to see the Aurora Borealis. And it was great the week before and great the week after, but in the middle of it, not so good for me. So I decided to come again and try it out this way. Come this way, maybe it works a little better. I seem like I'm a little loud. I think I'm loud for everybody. Okay, leave it alone. I can't hear you. Anyway, so I'm going to talk about the Aurora Borealis. I don't know if you watched some of the pre-shows, but there was some from the space station, so I thought you might like that perspective of what they see on orbit. And there's a lot of towns and things that you can see, I think, are in there. So what I'm going to try and do is tell you a story, and hopefully it'll all fit together. So I'm going to take you from a little bit of myth and things about the beginning of the Aurora Borealis, and then we're going to go all the way to where it begins in the sun, and we're going to come back all the way to the end. So kind of be patient in the middle. I'm going to kind of explain how the stuff that makes the Aurora Borealis gets you. So you might have to hold your breath through a little bit of it. But we'll see what we got here. I can't look that way, so I'll kind of stand here. So this is I'm going the wrong way. This is actually a live view in Iceland yesterday. It's a live view yesterday. Great picture of the volcano. So we did have this one, so that was like a week ago. So that's real time. No, it's not. So I was hoping to see that. I actually booked a helicopter ride, and then I found out how much the helicopter ride cost, and there was no lava flowing all over the place. So I thought that was kind of odd. All right, so there's another quick topic I want to cover. The Perseid meteor shower is the bulk of it is going to be the 11th, 12th, and 13th. So if you want to get up at like 3 a.m. and go on the helicopter deck, I probably won't be there. But I have gone up and I have seen a couple of meteors and a couple of satellites, and I have nice little pins if you come up and we spot a satellite together or something like that. I'll give you membership of the Satellite Hunters Club. So these are, when you see a meteor, I'm off topic here, but the colors that you see are because of the chemicals that it's made out of. So different like copper. Same thing when you see fireworks, and the colors come from different materials that are burning up. And one interesting thing that I found out in this research is some of the meteors that you see burning up are like the size of a grain of sand. And so it's amazing that you can see something that small. But we get hit like 17,000 times a year, so not too really worried. And when you go out to look, I know this is kind of a busy chart, but you're going to look northeast and you're going to find Cassiopeia. I'm sure all of y'all know how to find that because it's in the green line there, so we'll just go to that. And if you've got really good ideas, otherwise you probably can see the Andromeda Galaxy, which is going to get in a fight with us someday, but you'll have to wait till my Hubble presentation to catch that. And these are the sunrises and sunsets, so 6 a.m. Again, I won't be there, so I may. All right, so just quickly a little bit about me, and I'm not going to read these charts verbatim because I really don't know how to read. I'm an engineer, that's why I went into engineering, so I didn't have to read a whole lot. So I grew up in Titusville, Florida, which is near Kennedy Space Center. My father worked out there for many, many, many years. As a kid, I grew up, we would go down and watch the Apollo launches. So after going through this and seeing some of that, it's not really a big stretch to figure out that you wanted to be an engineer. I mean, if you take a kid and you put him on a fire engine, he's going to turn into a fireman. So, which I did, by the way, for when I was in college. I was Santa, and they brought me on a fire truck. And had to add a few pounds, like 100. And yeah, I probably am a rocket scientist. I've been a rocket. So what are you here for? What am I supposed to be talking about? Yeah, I'm going to try and get back on track here. So this is the Aurora. There is an A in NASA that I get to talk about aerospace. So one's there for administrative purposes. So. National Aeronautics Administration. Okay, so not that one. How about this one? It's not real time set up. So that's hopefully where we're going to get to by the end of this presentation when you understand why they're there. So to start out, through history, the Aurora Borealis, people see things in the sky and they try and figure out, what the heck is that? And so they make up whatever they want to make up. And so sometimes it's a good omen, it's a bad omen. So depending on where you're from, it's anywhere from your ancient ancestors up there to people you've slain in battle to spirits and stuff like that. So different cultures have different viewpoints on what it is. Some good, some bad. Hey, good harvest is coming if we see it. When in reality, it's just the lights in the sky. So whether it's good or bad or whatever, you can decide on your own. You just take a look back at it. But in general, it's just really cool to look at. I find it interesting, and why I talk about the slide a little bit is that you don't have to be afraid of something you don't necessarily understand. So there's a lot of things that people don't understand, and people yell and scream. It's like you don't have to be afraid unless it's your first day of engineering college where you just showed up and you're in calculus class. Be afraid. There's three of them. So that was tough. It took me 6 tries to get through them. So. All right, so Aurora Borealis, their lights, they have it on the southern pole and the north pole. So there's Australian lights, there's northern lights. They come from, I think it was coined by Galileo. I think it says it on there, but I can't read from here, and I can break my neck if I look up there. So, but they last anywhere from a few minutes to hours to, they could be there for days, but you can't see them during the daytime. So a lot of things have to line up, literally line up for us to get them, and we'll cover that a bit too. But it's like the Roman word for, read here, the dawn and the Greek word for wind, and they put them together and they come up with something neat. So, and we've gone back and found, paintings and things. So back in the 1500s where people have seen paintings that may, I guess that looks like, maybe this is a comet over here, I don't know. So just to give you a little historic viewpoint. So then they found some things in caves up to 30,000 years old. Now this could be just somebody scratching on the wall, I'm not taking out the trash, something, but there seems to be a few of them, and I don't really know, but you guys have to judge for yourself. But if it showed up like this, okay, I'll give a little more, I think they got some animals down here or some stuff up there, maybe, but then you run across cave things like this, and you're like, okay, so what's that? So, I'm kind of thinking it's a family portrait. Probably my family. At some point, my kids definitely have more arms than I do. So. All right, so let's get down to work and try and understand where the Aurora Borealis comes from. So the first thing I'd like to do is get a distance on size. Can I get 2 people to help me? All you have to really do is stand. You 2 want to help me? Who wants to help me? Come on up. Just stand over here. That's pretty much all you're going to have to do. You want to help me? Come on, just stand there. I'm a little further over this way. One of you right here and one of you on the other side, same spot. So when you look at things and how far they are away, the first thing you have to do is, how big is this stuff? Because all these Aurora Borealis lights have to come from somewhere, and it takes them a long time to get here. So if you boil down the Earth to 8 inches, you could fit 4 moons across it. So you're going to be the Earth. And this is the distance from the Earth to the moon. Get that clear? So, and this is the size of the moon, scaled down to 8 inches from 8,000 miles in diameter to 8 inches. So the question is, how far away, this is 2,000 mile diameter, so how far away is it? So it's about 250,000 miles to it, which in this room is supposed to be 40 feet, but my string is over there that tells me all this, and it's all tied up in knots because apparently I don't know how to tie a knot. So it's about 40 feet away, so it's really pretty far. So if we look at the sun and we put it to that scale, you're gonna have to walk way over there. Keep going, going out the back door. Stop, that's good right there. All right, and so this would be one side of the sun, and this would be the other side of the sun if he was like outside. That's good enough. But this is how big the Earth would be, and the sun is that much bigger. You could fit 109 Earths to stretch across it. So that's pretty big. So the next question is, if we scale down the sun to 8 inches, you're the sun now. I know it's a big roll, but you can learn the lines real easily. So if you were on the sun, how far would the Earth be away? So put your hands up if you want to play and vote. As I walk from the sun, so every foot's about 13 million miles, so people that can calculate real quick can figure that out. Sometimes my signs up there betray me and tell the answer. So the question is, where's the Earth? The Earth's right here, on my finger. This is the size of the Earth. If, don't do that. See, he's already giving away the answers. See, this is not, so how far, stop when you think you're far enough away, when you think, nobody's got their hands up, it's not working. Anyway, so how far do you think it is? Here? I'll come back to the people with the right answer. Okay, this is the right thing. So it's basically 72 feet away, and you can't really see it. It's it's incredible amount of distance, 93 million miles, and by the way, right now we're at 94, because we're at the higher point in the period apogee of the orbit. All right, going the wrong way, nothing like going the wrong way. So 93 million miles. So this is an actual picture from Cassini spacecraft that used to be orbiting Saturn. They finished the mission and then they crashed it into the Saturn planet. But you can see the moon and the Earth go by, and you can see the size. So you two, thank you for volunteering. Come over here, and you can take a picture if you like. Well, I pay my workers, or at least some of them. Oh yeah, she's giving me back the sun, so I need that. I've got more shows. This I can get rid of, some use. Anyway, so now you can get a little idea of how big they are. I'm sure I'm going to run out of time. So when you see a rabbit, that means I'm chasing a rabbit. So if you look at the largest planets out there, so this is the sun over here. These are bigger suns that are out there. And if you stuck the largest one here, it would come all the way out to past Saturn, to all the way out to Uranus. So it wouldn't be a good day if we were here for that. So. All right, so we're going to look at the light. We're going to start getting down to, okay, we got to get back to the Aurora Borealis, quit chasing the rabbits. How does it get here? Got to do a little bit of science here. So there's two mechanisms where we make a real lot of energy real quick, and they're fusion, reaction, blow up kind of things. So the first one is fusing things together, and that is used for making, how the sun works and making bombs. So we'll stay away from that a little bit. And the other is fission, breaking them apart. So, like what I'm doing. So there we go. So we'll talk about the fusion first. I spent many hours of school going to this. Look at the technical difficulty there. So the sun takes lots of hydrogen, puts it together, makes helium, light, X-rays, energy, and lots of Aurora Borealis stuff left over. So fission is the process of pulling things apart. Don't really have a good plan for that. I mean, it's basically for, nuclear power plants and making bombs. So, but I think we kind of like to stay away from the explosive, nuclear device class, and let's not go there. But here's a simpler explanation that we'll go with for now. So that's close enough for where we're at, right? All right. So you can see that I had to go a little technical. Does anybody see anything strange over here? No, keep going. Over here. Put your hand up if you see something. Okay, who said smiley face? One of these pictures belongs to you. So can you come get it afterwards? All right, excellent. So we make lots of stuff. There's I actually can't read. So it's kind of like a nuclear explosion, but it's not. I mean, it's contained. A nuclear power plant isn't an explosion, but it is. It's a controlled explosion. So this is happening a lot, and when it does that, it makes all kinds of different kinds of X-rays and UV light, and all that light comes out, and energy as well, and particles and things of that nature. And it's happening a lot of times, so like 100 million quadrillion. I mean, you can't even count the number of zeros a second. So this is really, the explosions were highly underrated there that I showed a minute ago. But okay. Anybody recognize the quote? Somebody tell me. Come on, in space, no one can hear you scream. Oh, wrong chart. We'll get there. It's probably in the next chart. Let's see, this is what gamma rays did to Bruce Banner. So this is what I look like if I go to the buffet. Okay, so I think I gave my one line early. So one of the things to note is all this stuff coming to Earth hits our magnetic field in our atmosphere, and it doesn't make it all the way down, which is really good because this stuff is really bad for you, as you can see how it really affected me pretty bad. Anyway, so it blocks a lot of stuff. So when you're out on the beach, you don't turn into a piece of bacon. So that would be nice. I like bacon. All right, so lots of stuff. It's interesting to me when I read this stuff and I learn something. So the inside of the planet of the sun is much less cooler than the outside, and we'll show you that later. But we're about 2 million degrees inside the planet and much less outwards. Okay, so here's my thing. Does anybody recognize that quote? It's the same one as earlier. Hey, who said alien? All right, come get you a picture if you'd like. I have to give away all these pictures, so I got to come with more questions. All right. And if I can pull stuff up. Okay. All right, so we'll chase another little rabbit right quick. So the sun is kind of in a tug of war with itself. It's got this massive gravity field which is holding all that nuclear activity in, but it's also got heat that wants to make it expand. And so there becomes an equilibrium between the two where they fight each other, and they finally, they come to terms with each other. And you figure out that you've got a stable thing, and that's going to last about another 4.5 billion years. So when that happens, we'll be in bad shape. So anybody worried? So I'm kind of not too worried. So here's another question: how much hydrogen do you think it burns a second? So I'll have to have a hand if somebody wants to guess. I'll take 2 guesses. Who's got a guess? Come on, somebody's brave. How many? 1 billion tons? We'll hold that answer, 1 billion tons. So who's got another answer? Maybe it's closer, maybe you win a picture. How many? 11 what? I don't know how much 11 zeros is. Okay, so we'll say those are really close. So you two get pictures because you have the closest 2 answers. So 164 billion tons of hydrogen. You can come get these afterwards if you like. Is that okay? You can come now if you want, I don't care. So it only makes 160 billion tons of helium. So there's 4 billion tons of stuff left over to help turn our lights back on over here, which we receive, as I showed earlier, as heat, light, and stuff. So it's supposed to be billions. I retyped that just before I came here. Okay, it's 1 to 2. So who cares? So it is my first time through with this presentation, so good catch. Who were you? Who said that? You get it. All right, shoot my rabbit there, bang, bang, bang. pretty sure it's billions. So. All right, so this stuff starts out in the middle of a nuclear explosion, and boom. So it's got to get out of the planet, but it can't just escape. You'd think that it could, but there's all this gravity pulling it back in. So it gets grabbed and recombined with other stuff, and then it gets torn apart again, and this happens over and over and over and over again until it finally makes its way to the surface. And before I click the next picture, does anybody want to guess on that one, how long that takes to get to the light to get to the surface? I'll take 2 guesses.
8 minutes.
Okay, I've got 8 minutes back here. How 8.5 minutes? Okay, great, 2 good guesses. Again, like 5 years. I've got 5 years up here. Okay, so I got my 2 best answer was 8 minutes and 8.5 minutes. So when you get done, you can come down, you and whoever you are, you already got a picture. So you can come and get a picture, and if they're gone, then you just have to come and visit me at the buffet, and I'll find one for you because I brought some extras. All right, so very close. So it does kind of I'll cover it when I actually read the charts. So it does kind of bounce around and run around, but it's 10,000 to 170,000 years to get to the surface. So those are really close answers. So all of them are really close. All right, so once it gets to the surface, then it only takes 8.5 minutes to get to Earth. So then it's kind of free. And so 186,000 miles per hour. All right, so you can see it's kind of busy running around, bouncing around. So it's quite a long path, and it's random. It just happens to be who you run into that day. It's kind of like when you're going through the buffet. If there's a lot of people in front of you, it takes longer. If there aren't, then you get to eat everything. So let's get into magnets. Did anybody do this in school? Okay, everybody always see this in school. So magnets are cool, but not in this case. They're not cool. So they're in the middle of the sun. So we've got what it looks like. Now they stopped this image because it's moving. So this is a still shot of what the magnetic field is. And so this second one is also a still shot, but it's a video of one spot not moving, but the sun's spinning, so you can't take that. Okay, so what does that mean to us for this thing? Well, we need sunspots to make Borealis stuff. So all this stuff's got to work its way to the surface, and then it goes in these loops, and these loops, to be the spoiler alert for myself, these loops break apart. They're kind of like ropes, magnetic ropes that come back around. So where they come back and touch, that's not what we get. We get the ones that break. So that's how we get more lights. And you get flips north and south pole, and they're always in pairs. So along that sunspot line, there's a cycle to the sun. There's an 11-year cycle to how these sunspots have activity. And I've kind of been mapping that and watching it. So the more sunspots there are, the more activity. And so last year was the peak of our 11-year cycle, which is out here somewhere. So here's where we are now, and here was last year. So we're down here. So last year was the year to go see it. So if you want to come with me, we'll get a time machine, go back, and I'll actually go to the right day because I was the week before I came. So maybe I'm breaking my neck looking up there. So this is where we had the lights coming all the way down into people saw in the middle of the United States, they're like the Aurora Borealis, it's got to be a bad omen if you see them that far down, so it's not. So this is the solar activity. You can see specifically that we're looking for this to go up. This is last year, this is push that up. So and you never can tell. They've had double peaks, so we could just come in one day and we see a lot of sunspot activity, some big numbers, and these are the charts that map it, and we're looking for some M's and some X's to get that way up in here. Like we have some back here, but you got to get that up so they have a solar flare that makes a loop that it breaks apart. So that's what we're looking for. You can see this daily, but we're not seeing any real big numbers, which is not really great for doing Aurora Borealis. So you can see the different sunspots that they're mapping. They give them numbers all, so you can tell they're engineers that do this. And here we are way up in here, so the red is good. So we like it to be down here. We're going to roll this. So not only does it have to have a sunburst, but it takes 1 to 3 days to get here, but then it has to come by at night, and so it's not always nighttime when it comes by. So here's what they look like. What we're looking for is a coronal mass ejection. Did I say that right? Somebody shake their head. Anyway, are we doing time-wise? Okay, we're way behind. So basically what we've got is it's a realignment of the magnetic fields. When they don't really quite line up, then they blow apart. And I'm going to kind of jump through a little bit so we can get through some of this. But it's billions and billions. See, there's billions right there. So billions of tons of material that's thrown out. And you'd think the sun would run out of material after a while, but it's really, really, really huge. And it does pose a problem for things on Earth, like computers, and satellite systems, and transmission lines, because they pick up all this stuff. On the space station, which I've been on, it was on the ground. I've been in the space shuttle too, but it was on the ground too. So. Anyway, so it does pose a problem, and on the space station they have a safe room, but if they can go in to protect them. They are below the Van Allen belt, so they get a lot of protection from that. So this is kind of what we're looking for. You have a big bulge in the magnetic field, and this breaks, and that's what we see coming off here. So how do we see all this stuff? So there's got to be some reason why a NASA guy's standing up in here. So this is SOHO. I helped launch this, and I have a presentation of the launch, but I'm going to hold that to the end if we have time, if that's okay. It's not okay, but I like to throw launches, but we'll hold it to the end. Okay, we'll say we're going to hold it to the end. And we've got another one, the Solar Dynamic Observatory, and we've got stereo A and stereo B. So all these things are out in space looking at this stuff, and then we get images from it. This is what we're looking for when it breaks and it throws stuff towards us. And you saw how big the Earth was compared to this stuff. These are humongous flares. Well, now you get to see what the Earth is. There you go. So this is one of the spacecrafts and explains a little bit about how it works. So the spacecraft doesn't see in color. So you're not seeing the color. What the spacecraft does is it has sensors that look at different temperature ranges, and then it assigns them a color so we get the nice pretty. Same thing for Hubble. It doesn't see in color. It sees specific frequencies, then they assign them colors afterwards. And so what they've done is they've come across, and these represents anywhere from 1 million degrees to 6 million degrees temperature-wise, very, very hot. And that's what I was talking about earlier, that this surface is much hotter than the center. Kind of like a pot of boiling water, the water is 210 degrees, and the steam is way, way, way hotter. So this is a little bit lengthy, but it shows you, now watch for the temperatures over here. It'll tell you Kelvin is 270 degrees different than Celsius. So no difference really. So. 6 million degrees, 10 million. That's pretty hot. So these are different instruments that are designed to look at different temperatures. starting to make a sunspot there. That's what you saw the light was. Now what they're doing is they're layering some of the images on top so they can start to make a little more sense about what's going on. Specific images look for specific things. Plus they look cool. So that was a bit long, so anyway. So these are, last year was the Solar Max, and there's one this year, next time, right here on this ship. If you were here and the ship was here, the 12th, or the 13th or the 12th? Anyway, 12th, next year, Solar Max, right, pretty much close to where you are. If it comes over, you'll see this. This is one we went to Missouri where my father-in-law lives, and a friend of mine, he took some pictures, and these are what, so you can actually see the solar eclipse. You could see them. Well, after it went solar eclipse, you could take off your glasses and you could actually see these with your naked eye. Pretty cool. So we're going to get back to the magnetic fields because sometime we're going to get to Earth. So all this stuff is traveling to Earth, and so our magnetic field kind of protects us a little bit, kind of like, like the spaceships have, where they have shields that go on. So we've got our own little shield. Oh, I'd rather show it again. Oops. Wait. Something's going on. Wait, all right, what I push? Okay, move out of the way, Rabbit. Okay, all right, so we'll go on. So, sorry about that. Almost got the rabbit. Anyway, so we have our own magnetic shield protecting us around the Earth, and so we have some satellites that are out here, stereo A and B, and the other ones that I talk about are out there, and we get some imagery from those satellites, and that's how we're getting all this stuff. And I helped launch the one. So this is stereo A and B, and this is the Earth. Images that are laid up by more than one satellite. So stuff close to the sun will be one satellite, stuff further out will be different satellites. And they can get it in 3D because they've got opposite satellites. Finally, he gets around to showing us something useful. See, there's different satellites that take different spots. So that's okay. So now we probably ought to talk, finally get to the end here somewhere. So in order to have it, we've got to have quite a few things lined up here. So we've got to have, clear night sky, good skies, lots of sunspots, timing. It's got to be, the Earth's got to be spinning the right way, and then there's a lot of luck involved. So we're going to talk to the captain, and I'm going to call up some NASA favors, and we're going to make all this happen. So that's it. Whoa, wait, I'm not over yet. So there's still time for me to mess up. So this is when the colors come from this stuff coming in, being sucked down by the magnetic field, and depending on what it hits in the atmosphere, now this is a good thing, because when this stuff hits it, that means that's the end of the stuff, and it doesn't come all the way down to the ground. So it's still protecting us. So depending on what level it hits, and whether it's oxygen or nitrogen, depends on what kind of color you get. And it also has to do with, apparently our magnetic pole just moved quite a bit. Anybody know the answer to that? So it shifted quite a bit, so that's part of the equation too that's not in there. So, but if we have good days, they look, we get some pretty good views. So this is Australia, so we can take the boat down there, get the captain to take a little detour. Maybe if we don't see it here, we can take a quick detour to Australia. from ISS. I can see that. I don't know where this is, but I want to go there. So hopefully we'll see some stuff like this. This is on a boat. I don't think it's ours, but in Iceland looking. It's real time though. These people walk this fast. Hopefully we'll see that. And this is what it looks like when it hits Jupiter. And I have some pictures of Saturn, but I didn't bring them. All right, so I have some time for some questions, but before I take the questions, I think we ought to go back and watch that launch. Don't you think so? Let's do that. Go.
5,
That means it's going.
3, 2, 1, ignition, and liftoff of Soho and the Atlas vehicle on the international mission of solar physics. Roll program is in. Vehicle responses look good at this time. Listen now to Skip Mackey and central telemetry during the mission. All items look good. Solids very well. Atlas PU is active. Solids look good. All engines look good. Acquisition through the Jupiter Relay Station. Good. Everything is smooth. Second set has ignited. Both of them have ignited. Attitude disturbances were light. We have solid motogenesis of the first set. Second set continues to burn well. PU is working well. All engines burning nicely. 9 miles at altitude, 5 miles downrange. Velocity 1,249 miles per hour.
So I worked that launch. I was on console. George Dillard was the announcer. He was like 3 seats away from me. Skip Mackey was my boss. He's in the telemetry lab. He retired after 35 years, and he came in after he retired, and we said, "What are you doing?" He says, "Well, I've never seen a launch before." "How can you work here for 35 years? And he said, "Well, I'm always inside working, so I don't get to go outside." So he took great pride in that. So I'm going to try and, let's see, this is my schedule coming up, and don't do that one yet. And so you can see that if you want. So I'll try and answer a couple of questions. I'm sure somebody's going to stump me, but I got a couple of minutes here, like 4 or 5 minutes, and I give out stickers. Who can be a runner for me? I need a runner. Somebody that can move with no knee joints. You can do it. Come on up here. So what's your question? I'll try and repeat it, and then I'll give you a nice lie. Because there's current. So the question was, when you look at the Aurora Borealis, some of them look like ribbons. Well, the atmosphere is just like the ocean. There's currents. So there are rivers inside the atmosphere. And so what you really, when you looked at like weather forecasts for like, well, I see a lot of hurricane ones, and so we see everything going everywhere. So what happens is the stuff comes in, it hits that river of stuff, and it just reacts differently for how it's being blown around. He gets a sticker, so take some of those stickers and go give him a sticker if you don't mind. And I'll give you we're going to give her a picture. If I haven't used them all up, she can pick a picture. So, yes? So her question, I think, is, so she said she's seen the Aurora Borealis lights twice, and they show up much better on her phone than on her camera than in person. Well, you're just like these spacecraft are designed. They're designed to look at a broader frequency and have more sensitivity in your eyes. I mean, I can have a camera that can see ultraviolet, which we can't see. Bees can see it, or I can see temperature. You can look hot and cold. And so most of your iPhones are way more sensitive than your eye. And last year I was here and we held up our phones and we could see it. But you could, I'm like, if I want to watch it on the phone, I could just go watch it, my presentation. So she could stick. Anyone who asks me a question, you can give a sticker. And if they don't ask me a question, probably can still give one too. I have to make sure. So I can't see. Here's one back here. I would shoot you with a laser, but I'm not going to.
How is it that sometimes in the lower latitudes of the state, you see the light better than farther north? I was in Alaska last April. My pictures suck compared to people in Idaho.
His pictures suck. That's what she got out of this. So remember that long equation I put up there about how all these variables come together? It really just determines how big of a solar event we have. This is how much stuff is coming our way, and then it has to hit you at nighttime. And the thing that was happening last year was that there was really a lot of solar activity, and we were getting these spikes that were like up to C, then M, then X. Don't ask me what they stand for. I'm going to have to go read up on that. Anyway, I knew it one time. At 3 a.m. I think I did, but I don't know now. Anyway, so if you get larger spikes, so it literally is, if you see them down lower, which is this question, why did you see it better lower? That's because it just happened to have a bigger solar event. And by the way, I did show you one picture. It seems like it comes in a ribbon, so if it's down lower, then you might not see it up north at all, because it's all going down lower. So, all right, I'm going to go over here. Now, you people who sat in the back, I can't see back there, so literally I think there's only 50 people in the room, so. We can turn the lights up if you like. Maybe that works if I just say that. Let there be light. Nope. Well, she wants to know if we're going to be having a viewing party. Well, I asked about that, and we should put in a chip and go some money together and go buy them red lights, because they're not going to turn off the lights. So I've been going up to the heliport where there's less lights, but the problem is it takes 5 to 10 minutes to get your visual locked in, to get your light level down, and then one quick look at the light and it's gone. So, but I went out the other night and I saw, like I said, I saw a few satellites go by, which is, I have buttons for that. So if you find a satellite, or if you see the Aurora Borealis, I'll just run out of buttons. I'll just get them all soon. So I hope that answered you. Let me take one more question, then the rest of the questions are going to have to go back because my little TikTok over here is standing right at 50 minutes. And who's the representative for what? Oh, okay, so whoever you are, just yell out your question. I'll talk to you later.
So my question is, could you please go over how long it takes the northern lights to
Oh, okay.
go over from the sun?
Oh,
The roots are formed
I know that.
because that seems like really, really fast.
Okay, so the question I believe, and I'm going to interpret to what I can answer, is, we have these mass coronal events on the sun, and then it has to get here. Why does it take 8.5 minutes? Well, it's not light. It's stuff. It's like protons and plasma and little bits and pieces of whatever mass was on the sun that got ejected. Electrons, but they're not really, they're not really touchy-feely things. They're really small. And so it takes, depending on how big the event is, 1 to 3 days to get here. So when we look at that chart that I showed earlier in the activity, if we have an event, then it shows up 3 days later. So it's kind of easy to predict. And then they can go around and tell all the power plants, hey, be prepared for this might hit, because all the power lines act like antennas and suck all that energy in. So make sure electric bill go down, probably not. All right, I'm going to call it there because I just hit 50 minutes. And so anyway, thank you very much for coming. I'll be happy to answer questions if you see me running around the ship, or if you see me, you can always go the other way.